All right, so because we now know that we can use a normal model to model these sample proportions, then we can now tie in all of the proportions that we know about a normal model. So our easy ones are the 68, 95, 99.7. That's within 1, 2, and 3 standard deviations of the mean. So we would expect 68% of all sample proportions to be within 1 standard deviation of the mean. Or we know that 95%, that's a pretty large number, sample proportions should be within 2 standard deviations of the mean. So we should not be surprised if 95% of all various polls gave results that were near the mean but varied above and below by no more than 2 standard deviations. And that is what we mean by sampling error. So we use this word error not like a mistake. It doesn't mean you did anything wrong. It's just the acknowledgement that we know the data will vary and we know there's variability, and we can quantify that variability or figure out how much variability we would expect to see from one sample to another. And a poll is just a type of sample. If I sample 50 people and poll them on who they're going to vote for it, and I get a proportion of who they're going to vote for, that's in one sample. But if I get a different 50 people, I get a different proportion, just like we did with the tails in the simulation. What we would expect about 95% of all polls to be within 2 standard deviations of the mean. Better terminology for this is sampling variability. You will hear both sampling variability and sampling error. And it's just a measurement of knowing the sample proportions are going to be a little off from the population proportion, but we can measure how off we think they are. How good is this normal model? Well, the normal model gets better as the sample size gets bigger. And this goes directly from the binomial. Remember, with the binomial, we needed to have at least 10 successes and failures in order for us to use the binomial. We're going to have the exact same rule when we go to do this for proportions. Most models are useful only when specific assumptions are true. So there's a couple of things that we have to assume in order for us to do inference. However, assumptions are often hard or impossible to check. That's why we have to assume them. The 2 assumptions we need are independence. This sample must be independent, and sample size needs to be large enough. Now, we don't just go ahead and assume them. We do have a couple of conditions that we can check to help us decide if the assumptions are valid. So you know what happens when we assume things. You should all know that expression. I won't finish that. But we don't just flat out assume them. We do check a couple of conditions. Those conditions are the randomization condition, the 10% condition, and the success failure condition. So these 2 here are how we decide if our sample is independent. And the last one here is how we decide our sample is big enough. So up here we had 2 assumptions. This assumption here has 2 conditions. This one here has 1 condition. And that's those 3 conditions. So the sample should be a simple random sample. It's not always going to be a simple random sample, but it should have some element of randomization. The 10% condition, the sample size N must be no larger than 10% of the population. This is how we decide that our picks without replacement are independent. If you guys remember back to that skills check where we were picking M&Ms from a very large supply, so what we were assuming there was our sample size was less than 10% of our population. That made our picks virtually independent. Even though we were not replacing the M&Ms back into the pot. Since it was a very large supply of M&Ms, specifically our sample size was less than 10% of the population, then we could say our picks were virtually independent. And remember, we need independence. If your sample size is more than 10% of your population, then we have a violation on independence, and therefore we don't necessarily have an independent sample. And we have to have independence to use that normal model. The last condition is the success-failure condition. This is exactly the same as the binomial model. The sample size has to be big enough so that NP, number of successes, and NQ, number of failures, are both at least 10. That's the same as last chapter. So basically, we need a large enough sample, but that is not too large. It needs to have at least 10 successes and failures, but it needs to be smaller than 10% of the population.